So, welcome everybody. As you can see, I brought my 3D printer. It's actually working already, so you can watch it if you like, and also after the talk you can come down and watch it more closely. So this talk will be about algorithmic 3D modeling, language modeling, and visual programming using VRL Studio. So the idea is that we create our 3D geometries visually, and but still that we have the option to do it by programming, really, because most of us are programmers, right? Are you all programmers? Yeah, so most of you, perfect. So my name is Michael Hoffer. I work at the Goethe University of Frankfurt at the Goethe Center for Scientific Computing, and my research topics are creating visual programming concepts for complex simulation workflows. And my Twitter handle is Miosoft, so if you like to stay in touch and talk about visual programming or IoT-related 3D printing stuff, then please do communicate. Yeah. So how do we create geometries programmatically? There are some options out there where you use a professional CAD/CAM application or a 3D graphics software like Blender or Maya, where you can just draw the application, the geometry in the application, and sometimes they even give you the option to do some programming in it, but it's not a real programming language in most cases, at least not for the 3D modeling as we explain it later. There is one good application called OpenSCAD that allows you to program that. But it has a limited API and a limited programming language, so I thought it would be cool to just create your own application and library. So that's why I wrote the JCSG library and JFXCAD, which is a JavaFX-based application for doing that. And the basic algorithm works like that. You can union two objects, like you see in this two circles that become a unified object, then you can create the difference, like removing a small part from one circle. You can compute the intersection and also the hull around two objects. So that are the basic building blocks that let you create complex geometries. Like for example, this one here. I know it's hard to see because we don't have a camera here, but later on you can come down and watch it more closely. And the JCSG library itself is also open source. You can download it from GitHub. You don't have to use VRL Studio for it. It's just a regular Gradle-based Java project. And it can also export all the geometries to a JavaFX node. So it's actually quite easy to simulate what you code and also visualize it. So this is another example also created with the library. It's for a drone arm, so I built my own drone with it, and it's very neat to have it parameterized geometry defined in code, because all the inner structures can be changed easily, and you can change the infill and other parameters like the holes for engines and so on. And also you can use JCSG in VRL Studio, that we will show later in the visual programming part. And it's just a plugin, and you can use Groovy and Java to access the whole API. And of course, you can download examples on the webpage if you're interested. Here are some images how you do that. There you see the algorithm again. You can union, difference, and intersect it. So and you can also create quite complex objects. So now I'd like to give just a brief introduction to 3D printing, because I apply all the visual programming to 3D printing here at the conference, because it's a visual thing, and it's really nice that you can actually touch the result of your programming. So who of you has done 3D printing already? Okay, quite a few, yes. And all the others are just interested in it and like to buy one, or? Yeah, cool. So additive manufacturing is actually a really exciting technology, and I just want to briefly explain how it differs from subtractive manufacturing. So in subtractive manufacturing that we do for quite some time, actually you have a raw material and then you want to extract an object from that. So like in this case, it's just a cylinder and you get a lot of waste because you're just removing material. And after that, you get your finished object. So this has advantages and disadvantages, of course, but it's also limiting because you cannot remove something from inside of the cylinder if you want to keep it closed. It's just not possible. With additive manufacturing, there is a lot more possible with it. So in this case, with this printer, you just use a filament and then you heat it up and you put small layers, one layer on top of another. And then you build up the object, you don't have waste, and you can even print holes inside the cylinder if you like, or any other object. So like you saw with the drone arm, for example. So because we don't have a camera here is a 3D printer in action. It just prints a very basic part for a Raspberry Pi based robot. And that's also a very cool thing to do with 3D printing, like combining it with IoT related stuff and also use it for teaching actually. Here are some nice microscope images where you really see how the structure looks like. And that was actually fun. It's a friend of mine who has access to an electron microscope. And when you go too far, like you see in the lower right image, actually the plastic starts melting again. And it's really weird. So it looks like volcanoes or something. And still interesting that you can see the layers also on this very small level. So the printer works really accurate. Yeah, of course, there is Thingiverse where you can share 3D geometries, and almost anything has done already. So when I started with 3D printing, actually I was kind of frustrated because everything was there already, but then I discovered, of course, you can do new stuff, and it's a really nice platform. So now let's go into visual programming, because that's what we want to combine. We want to do visual programming for creating 3D geometries. And first, I'd like to give some historical motivations why I designed the visual program environments the way I do. The thing is, when we did application development for the last decades, it started as a really hard and manual process. So people used punch cards to edit source code, and it wasn't interactive at all. So you didn't get a response from an IDE or even a very simple text editor like VI or something. It just wasn't possible. And computers were not able to run an editor and a compiler or even the program at the same time. So that's why we have these distinct phases, because people thought, okay, we have to first edit the program, then go load the compiler, create binary representation of the program, and then finally we could run it. But actually, that's not the only way to do it. So nowadays, we can do a lot more with it. And for historical reasons, people threw away all the useful information that is inside the compiler. So you would just create an application, use the compiler information, all the internal representation like the AST and everything else like the optimizations and so on. You used that for creating compact and efficient binaries, but after that you just threw that away, and when the program runs, you don't know anything about that anymore. Of course, there are exceptions. Nowadays, languages have access to AST, and we also use that in IDEs while developing to just enhance the experience, and also with programming languages like Groovy, they give you access to the compiler, so you can even do meta-programming in the language itself. But still, it's not that much used for the end-user application. And that's what I really would like to do. And this is also part of my research. So there are two approaches. You can do visual programming at runtime or at compile time. So doing it at runtime is a nice thing. It's basically something like a visual shell, maybe. So with VRL Studio, which is a really nice experimental, innovative IDE for prototyping and also learning, You can do visual reflection, so you give it source code and it will instantly create a user interface for you. And you can define workflows, and of course you have an integrated editor with syntax highlighting and plugin system and so on. What it actually does, the VRL framework below VRL Studio gives you a framework for automatic user interface generation. So you just give it source code, it creates a UI, and then you can do workflow management. So we have an object inspector that uses the reflection API to generate a user interface, and then it delegates that to the actual scene graph or JFrame, depending on which UI framework you use. So yeah, I'm not going to talk that much about plugins, but we have, of course, a plugin system, and we didn't know about Project Jigsaw when we started that. It was a few years ago, so actually we also have strong encapsulation there, and you can access the platform on different levels. And we also have native plugins, so you can bind your C++ frameworks as well. So now I'd like to give a short demo. This is a workflow, actually the JCSG one. So here you see we have a cylinder creator and a sphere creator, and that are just library objects that are automatically visualized. And they can have data flow dependencies to other objects, and here we create the union, the difference, and intersection. And the very cool thing is you directly get feedback from that. And then we can save that to an STL file and feed it to the printer software and just print it. And the basic concepts behind VRL Studio are actually that you get an instant visualization, so you don't have to stop the program. That is what I mean when I say we have to combine compile time, editing, and runtime to get more out of our applications. So when I compile this and create an instance, here is my user interface. I can directly use it. There's no build script or anything involved. You just type your source code and you directly get a response. And we can also do that with more complicated objects. Let's do something like this. Still very simple, but it has an output, so we just add two numbers. We get this representation, and the very cool thing about it is that we can now do data flow-based programming. So, like here, we can combine both, define a data flow, and we can instantly try our source code and see whether it works. And all these input fields, they have also validation. So if I type something that is not an integer, I run it, I get an error message down below. It says I can't invoke the method because the data input type doesn't match. So that's the basic concept of it. And all the object states, so this is an object that really is on the heap. You can serialize it, and whenever you save a project, it will be serialized, and all the object state is either saved as XML or base64 binary representation, depending on the object type. So now let's look at some more complicated examples. And I look what we have in the slides. Yeah, that's correct. So here we have another example where we actually did everything by coding. So you can just use the JCSG library as any Java library and use it in this Groovy code editor. And as it returns a CSG object here, it gives us this nice visualization. So and then we have a double, which is like the radius, and then we have the number of arms, so I could change that to 5 maybe. So like this, because otherwise it looks like a Mercedes star. And yeah, you can annotate everything, and then you basically enhance the information from the reflection API. So and all you saw here is open source. It's a project that you can contribute to, or you can just use it for teaching Java or doing experiments yourself. And it's not limited to 3D printing. It's just a neat application. So here is the web page, vrlstudio.mihosoft.eu. You can download precompiled binaries, and you can also check out all the examples, Like you can even do sound generation and OpenCL programming and a lot more. So that was runtime-based programming. Do you have any questions about that? Because actually the talk is split in two parts, so I would just prefer that we use the time between the talks as a Q&A for the first part if you want. Or should we, yeah, go ahead.
Go ahead.
Okay, go ahead. So now we come to visual programming with compile time. So we are not doing it at runtime, but at a compile time of the program, and edit time, actually. And therefore, we need language models. So the idea here was to capture not only the interface of objects, but rather than that, the whole program, actually. Because that is something that most visual programming environments struggle with. They give you a nice interface, you can edit many things, but then they save it as XML file or whatever, and it diverges from the actual source code. You won't find a really good visual programming language for Java, for example. There are editors that let you do some modeling, but it's not like editing, compiling, and running the program. So therefore, I introduced a language model that takes the AST from the Groovy compiler and is actually observable and can do communications with the user interface. And also you can declare and modify the model. Actually, you can declare new classes and methods and invocations to change the model, and it can render back to source code. And also, you have the programs as data structure, so you can actually add your own optimizations or transformations also in this model, except that it's also visual. And that is something that you see here. So here you see just some Groovy code, and on the right-hand side is really the representation of the complete program, even with all the intermediate values, because everything you see here will be instrumented. Here's a closer look. And now it's time also for a demo of that. At the moment, this is still a prototype, but you can also download it from GitHub. It's in an experimental branch, and then you can just run it. It's also a Gradle project, so I do it with NetBeans, but you can also do it with other IDEs. What you see here is just a very small program. It executes a few loops, actually 3. And here you see the complete program on the right-hand side. So if I select things in the editor, they will be also selected in the UI. So they are really tightly coupled. And if I run that, you will get instantly the profiling feedback and also code coverage, because every window that really gets highlighted will be executed. And now to something even better, like this one here. In this example, we really use the JCSG library again. So first, we create a sphere, then we create a cube, and then we do the difference operation between the cube and the sphere. So let me just highlight that. So you see it here. It selects all the windows that represent this executions. And then in the main method, we just execute the create difference once. And just to show you that the link between the UI and the source code is really deep. So what we see here is just a print line that you can see here. And I can change it to hello, Java, and Groovy. And also the source code will change. It's cool, right? So you can really do visual programming, and it translates back to the source code. So if I delete this, it will also delete the source code. And of course, I can add it again. If I save it, here it is again. And now for the instrumentation part. What it does, it takes the whole language model and introduces event generators before we execute things like methods or operators, and after that. And when we do that, we can run the program again, and we see all the intermediate results. So that's what we see here. So here is the create diff method. It's red because it takes all the CPU time. Everything we execute is actually executed in this method, so naturally it takes most time. And everything is visualized with JavaFX and JavaFX 3D. We can even zoom in. That's the result we get. And when you see that here, this could actually be used as a even end-user interface. You could just combine those and give it a front panel and then ship it as application. And users could either work with the UI or go back to the source code and change it. So it wouldn't really matter. And when we want to know what the create difference method does, we just go here. It's like that. Here we create the cube, then the sphere, and then the difference. So when we do algorithmic 3D modeling, this is really important because otherwise a debugger, for example, in a regular IDE would never tell us that actually the sphere was too big or too small or something. So we really need the visual feedback. And also humans are actually visual. We all always work visual, and when we do programming, of course, we train to think in different ways, and we kind of guess the actual control and data flow, and IDEs tend to help us by visualizing different references of the same variable and so on. But still, we are visual, and it takes a lot of time to really get to the text-based representation. But of course, there are also situations where text-based programming has its advantages, and that is why I think we should combine that so it doesn't really make a difference. So we should create user interfaces in a way that they are really the source code, and we use the programming language actually as our DSL in a way to define the user interface. Because everything I did was writing some Groovy code, and I got this user interface. So this is a DSL for describing a user interface that can do 3D modeling in this case. And you could do a lot of other things like image filtering or all sorts of applications, actually. So this is a research project that I do just to explore these possibilities. And yeah, as you can see, it's highly interactive already. So we could also introduce like a second create diff here. Something like that. And of course, it has to recompile, and now we get a second create diff window. And if we run it, it looks like that. Of course, I didn't change the numbers very much, but you can see, if you look closely, this here wouldn't be printable because it's not connected anymore. And no debugger would ever tell us, but we can see it instantly. So we can just change the number back to maybe 8 or something, so we get a connected object again. So here you see the difference. Okay, so that was the demo. I already mentioned that everything I did was actually also profiled on a language level. Maybe it's a good idea to just show you the instrumented version of the program shortly, briefly. It's here, so it is actually a mess, but it still executes what we wanted. So it introduces a lot of intermediate variables and takes apart all operators and everything. And the very cool thing about this, doing it on a source code or model level even, is that we can just apply it to places we want. So we don't run the JVM in profiling mode or debugging mode or whatever. We can even just change the level of profiling. And when we add different language supports, we can even render that language model to a different language, and all the instrumentations would still be there. in a different language. And we could even apply it to like HTML5 rendering or something like that. So, but at the moment we use JavaFX, and the really cool thing about it is that it's quite easy to implement these scaling capabilities. So what you see here is that some of the user interfaces just vanish when the objects get too small. So if I make this smaller and resize this here, the content is gone. So you can really visualize vast amount of data. So that is also important when you visualize real programs and large code bases. And what I'm thinking about is even extending that so that you can actually zoom out and not just visualize one file, but a whole project, or even relations between different projects, so that you can really scale from something like a group of GitHub repositories down to individual source code lines. And yeah, that's kind of the idea. And we are also working on integrating that into different editors and so on. But this is still an experiment. I would still be glad if you want to contribute or have ideas how to improve that even further, because it's still an experiment. It goes way beyond the paradigms we usually use when we do visual programming, like in LabVIEW or other languages. So that was basically the introduction to this environment. And here you find some resources. So VRL Studio can be downloaded. Here is also my Twitter handle and GitHub name. So yeah, there you will also find all the repositories and experimental programs. And now I like to open Q&A. So you can even you can come down and have a look at the 3D printed stuff, also at the robot that we built with that environment and the printer, and we can just have an interactive Q&A session. You can also ask via Twitter, just as you like. Because this was also about 3D printing, and many people said it was interesting to watch the printer, and sometimes it was crowded at the booth, so we thought we'd bring it here and you can just have a look at it and either, ask questions or just watch it. It's really fun. It's unfortunate that we don't have a camera, so if you're interested, please come down, have a look. And also I will show you the robot parts that we did. Yeah. Thanks. Yeah.
Quick question. Which libraries did you use to make the tool? And is it JavaFX, the graphical part?
So in the VRL Studio thing, it was Swing, an enhanced version of Swing. And then with the zoomable experimental thing, it was JavaFX because it has a very nice scene graph API. And we used JavaFX 3D for the 3D models. And the JCSG library can just export any intermediate object into a JavaFX 3D node. So you can directly visualize it. And that's what we do with the instrumented source code, where it puts in the 3D nodes there, and we just add some mouse listeners so that you can rotate and So you can also just use the JCSG library and add it to some JavaFX application. Actually, we also have an example for that. Just let me show it to you online. It's on GitHub. And here you will see the Pi on Wheels project. And here you see, you can do the coding here. And also you see the 3D visualization, which is just a JavaFX 3D node. Does it answer the question?
Did you consider using a rich client platform like the NetBeans one?
Yeah, actually, Gert-Jan from NetBeans, he already started an experimental plugin for the NetBeans platform. So that is actually also the goal. Also with the new approach, it would be preferable, because then you had a really powerful text-based editor and you still had the visualization for free. You could just do it with any NetBeans or project, or also for other IDEs. So I want to start with Gradle, actually, so that you use the Gradle tooling API to do that. But we're also looking into integrating that into NetBeans. That's a good idea. Yeah. Yeah, you can come down. As I said, don't be shy. It's rather difficult to see you, so maybe I missed somebody. And if that's the case, go to the microphones upstairs or just come down.
So what's the main difference between this one and OpenSCAD?
The difference is that this runs on Java, and as I do the visual programming with so the question was, what's the difference between OpenSCAD and JCSG? So the difference is that this one runs on Java. We can use reflection to do all the visualizations automatically. In OpenSCAD, only gives you one result. It's a very good library and much enhanced, but it doesn't give you all the intermediate results. You only see one object, and you cannot visually program. So that's just a limitation because they have a limited language, and also you cannot do any kind of programming. What I can do here is we also have simulation frameworks, and they give you an output from a simulation, and I can just feed it to the JCSG library and the other way around, and I can do it with reflection, so I don't have to create all the user interfaces. Everything is completely automatic, and you don't have a specific user interface for OpenSCAD. But what you could do is also you could actually add a Java layer to OpenSCAD, and then you could do basically the same. But for my experiments, it was better to write my own lightweight library because it doesn't depend on C++ and Qt and whatever. And also I had some licensing issues with OpenSCAD because it's pure GPL, and I tend to release stuff under BSD or Apache stuff. So but I really like the program. So yeah.
I'll try.
Yeah.
I find it also a great application for teaching purposes.